See, we are going to see the properties of determinants. Previously, we have seen how to take a determinant of a matrix. Determinant is a value of the matrix, that is a single number. Okay, like matrix is an array or arrangements of numbers. Okay, but determinant is a single number. So based on that, while taking determinant, we might face some challenges. So like the question that you take and write 1990, 1991, like all the numbers are very big, then what we have to do. So in that kind of situations now, these properties are going to help us. So there is only 10 properties, like they are going to act like a formula. Whenever we got stuck in a question, we might use any of this and we make it simple. That is the idea. Okay. So the first property of the determinant is, see, the determinant of a matrix is equal to determinant of its transpose. Okay. If you take transpose of a matrix, still the determinant is equal. Okay. And the second one, that if determinant of a square matrix, like this matrix, let us say some A1, B1, C1, A2, B2, C2, A3, B3, C3. So here, suppose if I am interchanging a row or column, simply I am just misplacing the determinant, like A1, B1, C1, let it be. I am bringing this R3 to R2. So A3, B3, C3, A2, B2, C2. Then what will happen means, that determinant value also same like determinant of A, but with a negative sign. Okay. Okay. Simple change. If you interchange a row or column, one place, one row or one column, if you interchange means the determinant will be negative. For this, for example, this determinant value is 5 means this determinant value will be minus 5. Okay. The same way, see, that only works when interchanges. Okay. And the third property. If two rows of a square matrix are identical, then value of the determinant is 0. If two rows or columns of a matrix is identical means what? They are same numbers. Then the determinant is 0. So, like this A1, B1, C1 itself will take A2, B2, C2. This also will be equal to A2, B2, C2. Then we get two rows are equal, right? Or suppose we get two columns equal, also the same thing. So this A2, A2, this is B2, B2, C2, C2. So this determinant value is what? Obviously 0. Okay. Clear? Why? Because simply if you take A1, that minor if you take means B2C2 minus B2C2 is what? 0. See, B2C2 minus B2C2, 0. Same like for all the elements it will come. Okay, that's why the determinant value also 0. And then the fourth property, if all the elements of a row or column of a square matrix are multiplied by a number k, then the determinant value of the resulting matrix is equal to k times the determinant value of original matrix. So, like if any one row or column, each elements multiplied with k, then the resulting matrix determinant will be k times the determinant of A. Like if you take the matrix A as the same one, A1, B1, C1, A2, B2, C2, A3, B3, C3. Suppose I am multiplying this first column or second column, any one column or one row, I am multiplying. Then we will get some other matrix. That matrix is what? Some k into A1, k into B1, k into C1 by this one A2, B2, C2, A3, B3, C3 will be there. So this matrix determinant is, we don't need to calculate separately. Okay, suppose we identified that all the entries are same, but one row or one column alone, just the multiple of this row or this column means, we can simply put this is equal to k times determinant of A. This matrix determinant alone, if you find, means enough. Okay, that is the idea. Shall I erase this? Second one is what, if any row or column interchanged, then determinant value is negative. I will write if any row or column interchanged, then the determinant of A equal to minus of the determinant of A. Determinant of the new matrix, right? After interchanging, we'll get a new matrix. Okay, that matrix determinant is simply negative of the previous. Okay, and then the fifth property. If the elements of a row of a square matrix are k times the elements of another row, then the given determinant value is 0. Shall I erase this? Like everything, shall I erase? Okay. So there is the second one as well. Okay. Fifth one. See, what we are discussing only about square matrix. See, in a square matrix, if any one row or a column is multiple of other row. Row means multiple of other row, column means multiple of other column. Then the determinant is 0. Why? You see the matrix, this is A1, B1, C1, A2, B2, C2, A3, B3, C3. Suppose this all B1, B2, B3 are K times C1, K times C2, K times C3. Then using the previous property states what? If any row or column is a multiple of a number, then the determinant value will be what? K times the original determinant, right? No, not 0. K times the original determinant. What is original determinant? A1. This K will be taken out. C1, and this is A2. C2, C2, and this is A3, C3. Now, the previous one, what it says? If any two rows are identical, then the determinant value will be what? 0. So, here two columns are identical. So, we get the determinant value 0. So, that will become K into 0. That is why we find any multiple like this A1, B1, C1 and all confusing means, we will see with the example numbers. So, let us say some 1, 2, 3, 4, 5, 6 and 2, 4, 6. Now, if you see clearly, what you can see, any row or column is a multiple of any other. See, if you multiply first row with 2 means you will get the third row. Is it? So, if you notice this even, that is enough. So, okay, 1 into 2, 2, 2 into 2, 4, 3 into 2, 6. Okay, they are multiples. So the determinant value is 0. We don't need to calculate 1 into this one minus 2 into this one plus 3 into this one, like we don't need to calculate. Simply by observing it we can say. That's what this means. Okay. Any row or column. But you should observe clearly. Okay. And the other property, sixth one. Okay, that brings us another note as well. That note is nothing but if A is any 3 by 3 matrix, and K is any number, if you multiply the matrix with K, then each row and each column will be multiplied with K, right? Then for this one K can be taken out, for this one K can be taken out, for this one K can be taken out. So totally 3 times K can be taken out. Okay. Okay. So suppose you find a matrix like 2, 4, 6, 10, 5, 20, no not 5, 10, 8, 20 and then 12, 14, 16. This like one matrix is there. Okay. What do you observe here? All are multiples of 2. Okay. Is it or not? So this can be written like 2 into this matrix. What? 1, 2, 3. This is 5, 4, 10 and this is 6, 7, 8. Okay. So this is what K into A means. So while calculating the determinant, like this is the matrix I written. While calculating determinant, what we can write? 2 cube into determinant of this matrix alone we can calculate. See, these are comparatively big numbers. We cannot able to calculate. But here they are small numbers. We can easily calculate. With the answer we can multiply the 2 cube. That is the idea. Okay. Or you take like this. This is what, let me extend this property for somehow. This is like 12, 15, 21 let it be. So from the first row we can take 2 as common, like using this property. Okay. The same way from this row also we can take 2 as common. From this row we can take 3 as common. Okay, it is not that we are taking common, we are applying this property, but just to get us understand I am saying all this. Now the matrix will be what? Into determinant of like this 1, 2, 3. This is 4, 5, 7 and this is 6. They are multiples of 3, right? That's why I am taking 3. Okay. And this is 6, 7, 8. Like this alone we can calculate the determinant and we can multiply these numbers at last. Okay. That is what this property is about. Like while solving the questions, these all the things should strike our mind, what we can do like. So this is the 6th property. And the 7th one. Sorry, this is the 5th one, right? 6th one we are about to see. If each element in a row or column of a square matrix is sum of the terms and its determinant can be expressed as the sum of the 2 determinants of 2 square matrices of same order. Shall I rest this? Okay. See, simply this is a matrix A1, B1, C1, A2, B2, C2, A3, B3, C2. Like one matrix we are taking determinant, right? So instead of this, suppose we have plus X, plus Y, plus Z. That we notice that this can be expressed as sum of 2 different numbers. Then the determinant value will be, so this is the 6th property. We can split this into 2 determinants. Like this A1, B1, C1, A2, B2, C2, A3, B3, C3, plus this along with plus some numbers are there, right? That numbers you can write. That numbers means this is A1 X C1, B1 Y C2, sorry, A2Y C2, A3Z C3. These two determinants can be separately calculated and they can be added. Okay. That is what this property is about. Okay. And then seventh one. If the elements of a row or column of a square matrix are added with k times the corresponding elements of any row or any column, then the value of the determinant of the resulting matrix is unaltered. That means, see, listen closely. If the elements of a row or column of a square matrix are added with k times the corresponding elements of any other row or column, then the value of the determinant of the resulting matrix is unaltered. So, you take a matrix, this is A1, B1, C1, A2, B2, C2, A3, B3, C3. Okay. So, any row or column, I am taking this R2. This R2 I am taking. See, this is like implies and implied way. That means you are writing the answer in R2. You are doing some operations here. The result should be written here. Okay. This is R2 row. In this, I am going to take the element of R2 plus k times the element of R3. Then what means? The determinant value will be, this is A1, B1, C1. Last row is unaltered. A3, B3, C3. But the second row I am changing. How I am changing? I am taking the element of R2 and the corresponding element of R3 that multiplied with k. So this will become A2 plus k A3. This will become B2 plus k B2. This will become C2 plus k C3. So if we multiply like this means, multiply and add or subtract like this means, the determinant value remains same. For this it is determinant of A means, this is also determinant of A. That means for this determinant value is 5 means, here also determinant value is 5. Okay. It remains unchanged. Like we are taking along any row or any column, determinant value is still same, right? That like. Okay. And that is the seventh property. And then eighth property. The sum of the products of the elements of any row or column with the cofactors corresponding to the elements of any other row is 0. See, the eighth one, you take the matrix, this A1, B1, C1, A2, B2, C2, A3, B3, C3. Okay. What is their cofactor matrix, you know? Cofactor matrix we write like capital A1, B1, C1, capital A2, B2, C2, capital A3, B3, C3. Recap, what is cofactor? Remember that minus 1 power I plus j into minor of that particular element. Okay. Now, how we are calculating the determinant, you remember? The determinant of A value is what? The first element in the cofactor of A, first element. Second element into cofactor of the second element. Third element into cofactor of the third element we are taking, right? Okay. But instead of doing like this, if we multiply the cofactor of some other element like A2, B2, C2, I am just changing. It is not their corresponding cofactor. Okay. First element multiplied with this element's cofactor. Like any row or columns corresponding cofactors. If we choose R2 means the cofactors of the elements of R2. The two corresponding elements cofactors. That like we are interchanging the cofactor means the result will be always 0. And that is no way related to the determinant of A. What's up? See, first row elements with the cofactors of second row elements I multiplied. Same way, first row elements multiplied with the third row elements cofactors A3, B3, C3. If I multiply means that result also will become 0. So the thing is, if you mismatch the cofactor on the elements means the answer will be 0. Okay, that is one property. This is 8th property. And then 9th one. So 9th one is what? If the elements of a square matrix of a polynomial in X, when X is equal to A, two rows or two columns become identical, then X minus A is a factor of its determinant. Similarly, when X is equal to A, three rows becomes identical, then X minus A whole square is a factor of the element. So simple, we get the matrix. In that matrix, all are like polynomials. Some A1 of X, B1 of X, C1 of X, and this is A2 of X, B2 of X, C2 of X, and this is A3 of X, B3 of X, C3 of X. Okay, this like polynomials are there. When you substitute X is equal to A, then what happens in the matrix is two rows becomes identical. So what happens when two rows become identical? Then the determinant value is 0. So we say X minus the substituted value is a factor of the matrix. Okay, is a factor of the is the factor of determinant of A. Okay. Okay. Then suppose three rows become identical. Three rows or columns. Whenever I say rows or columns also, anything. So become identical means, then we say X minus A whole square is a factor. Okay. Suppose it is a 4 by 4 matrix. You get all the four elements. So all the three rows become identical. Then which is a factor? So 4 by 4 matrix. We after substituting A, three rows become same, equal, identical. Okay. Then which is a factor? Don't say X minus A whole cube. X minus A whole square is a still factor. Suppose in a 4 by 4 matrix, after substituting A, all the four rows becomes identical. Four rows or four columns become identical. Then X minus A whole cube is a factor. Okay. Simple. How many rows become identical? X minus A, that number of rows minus 1, that is a factor. Two rows become identical means X minus A power 1 is identical. 1 is a factor. If three rows become identical means X minus A whole square is a factor. Four rows become identical means X minus A whole cube is a factor. Okay. That is the 9th property. And then 10th one. This property we have seen yesterday itself, like if A and B are two square matrix, then determinant of AB, that's all. It is not factor of the matrix, it is the factor of the determinant of the matrix. See, I kept the determinant of A of X. It is not a factor of the matrix. Okay. And the 10th property, if A and B are square matrix of same order, then this determinant of AB is equal to determinant of A into determinant of B. Okay. Also don't get confused. Sometimes they might say that is equal to determinant of B into determinant of A as well. They are numbers. Okay. But whereas in matrix multiplication, this AB is not equal to BA. That you remember always. When it comes to determinant can be interchanged because they are numbers. For this 4, for this 3, 4 3s are 12 coming. Then it is possible to interchange also, right? So don't get confused, don't get twisted for this. So all the 10 properties will revise once. After this we have several notes. So the notes, 11 properties, right? No man, I got only 10. You marked 11. It's okay man, count doesn't matter. 7. Oh, 11. Okay, you just match it with the book. You might notice the subcase of a property also, like another property. Okay. Okay, some notes are there. See, if nth order square matrix is there, means like k times the matrix, determinant of the matrix is k power n into determinant of A. That we discussed already. Like each row is multiplied with 2 means this 2 cube, this 3 by 3 matrix means 4 by 4 matrix means 2 power 4 will come. Okay. And the second one, if each element of a row of a square matrix is 0, then the determinant is 0. It's obvious. Like if all the rows are zeros means, look, the first row is full of 0. Then what is the determinant value, remember? 0 into something minus 0 into something minus 0 into something. Fully 0, right? That's what they say. Also for any positive integer n, we get the determinant of A power n is equal to determinant of A whole power n. Okay. Like you get one matrix, like this is 2, 4, 9, 16, 25, 36 and oh no, it doesn't work like that. No man. It's not working like that. Like the thing is, we can square the matrix and put the determinant, or we can put the determinant and we can square the matrix. That can be interchanged. Okay, that is it. And then, if a triangular matrix, if A is a triangular matrix, then simply for triangular matrix, either it upper triangular or lower triangular or diagonal matrix, where you went? Are you there? Are you there or not? Am I audible? Am I audible? Where you went in between? No. Okay. Then what I was talking about? See, for triangular matrix, the determinant value is simply product of the diagonal elements. Only for triangular matrix, not for the other matrix. For example, if you take this 2 0 0 7 5 0 2 7 8, this like one matrix is there. Okay, then the determinant of this matrix will be product of this diagonal elements. So simply 2 into 5 into 8, we get 80. That is the determinant value. That's all. Even if you calculate along with any row or column also, it becomes the same. Okay. That is what this note is about. And then to find the determinant values, we can use the operations like R1, taking R1 like R1 plus K times R2, that like we can calculate, because we have seen one property that the determinant value will not change. Okay. So now we will quickly revise all the 10 properties. See, the first property is about, if you take a transpose, the determinant value remains unchanged. That is the first property. And the second property is what? If you interchange any row or column, then the determinant value will be negative. Simply interchange any row or column, determinant value will be negative. And then third property is what? Third property is what? Identical. What identical? If any two rows or columns becomes identical, then the determinant value is 0. That is the third property. And then fourth one, any row or column multiplied by k, then the determinant value also multiplied by k. Okay. And if any row or column is k times the other row, like first row is 2, 4, 6, next row is 4, 8, 12, then multiplied by 2, next row came, right? So the determinant value becomes 0. Okay, that is it. And then fifth property is that one. And then sixth one, like each element of a square matrix is sum. Like suppose you get any sum in between, means the determinant can be splitted. And then the seventh one, if each element of a row or square matrix added with k times the other row, the determinant value remains unchanged. Like one row we are taking, multiplying the other row with some numbers, adding this or subtracting, that remains the determinant value remains unchanged. And then the eighth one, the sum of the product of the elements of any row of a square matrix with the cofactors, like if you interchange the cofactor, simply if you mismatch the cofactor of a row with the other row means the determinant value become 0. And then next one about factor. When you substitute, if it is a matrix of polynomial, when you substitute some number, the determinant becomes 0. Like two rows become identical means we get x minus a is a factor. Suppose we get three rows identical means x minus a whole square is a factor. Okay. Yes. And then for two square matrix of same order, the determinant of their product will be the product of their individual determinants. Okay. And the last property, that is the last property, right? Yes, that is it. Now, using this, we are going to solve the upcoming questions. Yes. Sixth property. That is sixth property, yes. Seventh is what? Any row is multiplied with some other row of k times means the determinant values remains unchanged. That one example also I did. So, you want me to explain this once again? Yes. Before that property. Yes. Yes. No. There will be an element. That element can be splitted like that. For example, in this matrix, you see this is 2, 7, 2, right? This can be written like 1 plus 1. This can be written like some 5 plus 2 based on the requirement. This can be written like again 1 plus 1 or 2 plus 0 you can write. Then this can be splitted like into 2. The first numbers and all will become some elements of a matrix. Second numbers and all will become elements of the other matrix. They can be added. Okay, that is different. Okay, now we'll see some solved examples. You have any doubts in this properties? See, in the question, they will not give use properties, this property, that property, they will not give. We have to identify what property should be used. Okay. So, the solved example 1. We have a matrix like a square plus 2a, 2a plus 1, 1, 2a plus 1, a plus 2, 1, and then 3, 3, 1. The determinant of this matrix is a minus 1 whole square, sorry, a minus 1 whole cube. Like we have to prove, man. Okay. That how we can able to prove. See, whenever we are approaching this kind of the determinants, like several things we need to keep in our mind. Like all the properties. Okay. We might think that, okay, this is sum of this, so this also can be written like 2 plus 1. We can split the property. As now only we have discussed those things. Okay. Am I audible? Visible? Perfect. See, like that we should maybe think. We can apply also. But the thing is, if you directly apply determinant also, the same answer will come. But it is quite heavy. It takes lots of time. So we might use the property. That is the first thing we need to understand. Okay. And after that, you see this one is what? Like any identical rows can be made or not, just check. By adding or subtracting one row element with the other row element, any identical rows or identical columns can be created or not, we should check. Also, any one row or column is a multiple of other row or not, we should check. Okay, these kind of things you should check. Okay, if nothing is possible, by using that elementary row operations, we call that those things are elementary row operations, like adding one row with the other row and all. By using this, we can make zeros as many as possible in the same row or same column. Okay, like in this, these two elements are 1 and 1. So while checking, after checking all those things, we must arrive at this condition, like 1 and 1 is there. These two numbers can be subtracted, we can make 0. So the determinant can be easy. The as many zeros you are getting in a row or column, the determinant will be easy, right? That many terms you have to work out. One element becomes 0 means we should work out only 2 elements. Like 2 elements become 0 means only one element minor alone we can calculate, we can make the process simple. Okay. So after noticing this one, we should make this as 0. So let me take the elements of R1. See this notation R1, this double arrow I kept, which means I am going to apply some operations here. The result should be written in R1 in the same matrix. What I am going to do? Simply I am taking the elements of R1, subtracting with the elements of R2. We can do. Okay. So to explain you, I am writing it separately. Once we are habituated, we can directly write. Okay. What is elements of R1? A square plus 2a. This is 2a plus 1, 1. And this is 2a plus 1, a plus 2, 1. We are going to subtract these things, man. When you subtract 1 minus 1, we'll get 0. And this is 2a plus 1 minus a minus 2. Here also minus will put. This is minus, because I am subtracting, right? I am just interchanging the signs. Now 2a minus a is a minus 1. And this is a square minus 2a. Sorry, plus 2a minus 2a cancelled. Then we'll get a square minus 1. Perfect. So this is the new R2. New R1. Instead of first row, I am going to write this new one. So we'll get a square minus 1, a minus 1, 0. Okay. And the second row is 2a plus 1, a plus 2, 1. Third row is 3, 3, 1. Okay. Now again, using the elementary row or column operations, we should make any one another element 0. I am making this, again these two can be subtracted, right? We can get one more 0 in the same column. Also, if you take the determinant along this column, that would be easy. So first make this, any one of this as 0. I am making this one as 0. Okay, what I am going to do? I am going to write the result where that we should decide first. So I am going to write the result in R3. Okay, in R3 I am going to write the result. How I am going to write? R3 minus R2. I am going to take the elements of R3 and the corresponding elements will be subtracted with the R2. Okay, so R3 elements and all what? Again I am saying for explaining purpose I wrote this and all. Even you are also getting difficult means you can write this as a rough work. This is the main work. Okay, we can even combine two operations into one also. Once you had asked, this is the very first question, I am just explaining in detail. Okay, now R3 elements I am writing, that is what? 3, yes. Yes? That is the question, good question actually. See, we have seen one property, remember? We can take any elements of the row. The corresponding elements of the row can be multiplied with the corresponding elements of the other row. Sorry, can be added or subtracted with the k times multiplied with the corresponding elements of the other row. And the determinant value is remains unchanged. Which property? Like 6th or 7th? Some property was. That property we have seen, right? So the original determinant remains unchanged, unaltered. Okay. We can add or subtract, that's all. Any row or element can be multiplied with a number also. Okay. Yes. We cannot do R1 into R2 and all. This is not valid. We can take the elements of R1 multiplied with 5 with R2 can be subtracted. That like we can do. Okay. Yes. See here I am simply taking R3 and subtracting with the elements of R2. So R2 elements are 2a plus 1. We should be very very careful while doing this. A plus 2 and 1. So I am going to put minus. So this is minus, this is minus, this is minus, minus, minus. So minus 1, 0, that is our A. Now this one minus A and this is plus 1 will come, right? Minus A plus 1. Why? Because 3 minus 2 is what? Plus 1. Number with number, variable with variable. Okay. And this is 3. Minus 2a. And this is what? Plus 2. Okay. It's not 4, man. See, it is not minus of 2a minus 1. Original element is what? 2a plus 1. As I am subtracting, I changed all the things into negative. Okay. Okay. Or else for this, you should write one more step. That is 3 minus 2a plus 1. Then it will become 3 minus 2a minus 1. Then minus 2a plus 2. Like that you should write. Okay. So now the matrix can be written like what? A square minus 1, a minus 1, 0. I think from this only we should write. And second row remains unchanged. Is it? That is 2a plus 1, a plus 2, 1. And third row will become what? This new row. This is new third row. So that is minus 2a plus 2, minus a plus 1, 0. We made two elements 0 in the column. Okay. Yes. A3 4 minus 2a. See, that's what I said, man. See clearly, I am going to take the R3. In R3 only I am going to apply the change. R3 element is 3 minus the corresponding element of R2 is what? So not here, from here. R3 element is 3. Corresponding element of R2 is what? 2a minus 1, right? Sorry, 2a plus 1. Sorry. 2a plus 1, right? Then when you subtract, 3 minus 2a minus 1 will come. Then numbers only can be subtracted, 2a minus 2. Okay. Okay. Any confusion still? Okay. Now you see, I made two elements out of a column as 0. Now remaining one element. Now if I take determinant along this column, this should be easy because two elements is 0. Okay. But while taking the determinant, we should be really aware of the sign of the cofactor. For this, I told you in shortcut, remember what it is. Simply put to positive, negative, positive, negative, positive, negative, positive, negative, positive. Okay, now plus 0 into something you should write, whatever it is, don't care. Minus 1 into, for this only you should take the minor. That is cofactor sign minus I kept. For this, the minor I taken means what it is. A square minus 1, a minus 1, 2a plus 1. Oh, sorry. Instead of without leaving this row and this column, right? These two elements, 2a plus 2. See, for your understanding purpose only, I kept that plus minus and all. Don't get confused while writing here. That is for cofactor sign. Okay. That is, and then plus 0 into something. We don't bother. Alright. So let us this. Okay. Now that determinant alone we should work out, man. That's all. So minus of, because this minus is there, these two elements will become 0. Now these two can be multiplied. A square minus 1 into minus a plus 1 minus, this is what, minus 2a plus 2 into a minus 1. Okay. Now you just simply multiply, or we can take things as common. What we can do? Multiply. Okay. Then a minus 1 can be taken as common. See, this a square minus 1 can be written like a plus 1 into a minus 1 and minus a plus 1 minus of minus 2a plus 2, and this is a minus 1. We can take a minus 1 as common from these terms. Minus of this minus outside, a minus 1 as common. Then remaining is what? A plus 1 into minus a plus 1 and then minus of minus 2a plus 2. Okay. And simplify this. That's all. So we get minus of a minus 1, and this is a plus 1 plus a into 1 minus a. This is it? What it is? 1 plus a into 1 minus a. So this is 1 minus a square, and this is minus into minus plus 2a minus 2. Then what we will get? Minus of a1 minus a square plus 2a minus 1, like we will get. Okay. And minus, this minus, we can take one minus as common. Why I am taking minus as common means there is a reason. This looks like a plus b whole square formula or a minus b whole square formula, is it? While taking minus as common, what we can say? So this is minus of a minus 1. Here we will take one minus, that minus into minus will become plus. Then we will get a square minus 2a plus 1. That is what? A minus 1 into a minus 1 square. What it is? A minus 1 into a minus 1 square? A minus 1 cube. Okay. That is what we need to prove. Also, when you notice that in your book, you have your book, right? In that book, are you seeing this question? That page number 73. Okay. In that, they have taken different elements, different rows, different things as 0. Okay. They made the elements of this first two elements as 0. But I made first and last one as 0. Intentionally I did. Why? Because just to show you that it is not depending on the same actions we should take, then only we will get the correct answer. It is not like that. One should have an idea. Like we should do the process correctly. That is it. Okay, it's about the idea. It is not about the same sequential order. We cannot memorize this also. Is it possible to memorize? Okay, a square plus 1, the question is this operation, this operation, this operation. No, we cannot memorize. So all we can take is only the ideas. That ideas you can execute. Okay, I don't get any idea. Simply, without even applying any of this, directly the determinant we can calculate. But the thing is, it takes much time. Because ultimately we want the determinant value. At any cost, we want the determinant value. Okay. So if you solve the original matrix, means it will take some more complicated terms. That is why we are using this properties. Okay. Any doubts on this? Or you want me to explain this once again? Okay. Now, look at that second question, not the second one. Take the exercise. In that exercise, now look at that question, man. That 1990, 1991. That's all. See, look at this question. Okay. Now is it all right? 1990, 1991, 1992. This is the question, right? We need to take the determinant. Is it? Okay. Is it possible to multiply these numbers and get the determinant? Yes, it is possible. It is possible, but it takes some time. Okay. Then you just think of applying any property that we studied. This can be written like 1990 plus 0. This is 1990 plus 1. This is 1990 plus 2. Okay. And this is 1990 plus 1. This is 1990 plus 2. This is 1990 plus 3. And this is also 1990 plus 2. This is 1990 plus 3. 1990 plus 4. Okay. And this can be splitted into two different matrices. Okay. How we can split? One matrix is 1990, 1990, 1990. Okay. Plus the other matrix is 0, 1, 2, 1, 2, 3, 2, 3, 4. Now we can take the determinant of this. This determinant will become 0, right? So we'll get only 0, 1, 2, 1, 2, 3, 2, 3, 4. See, again we can take the elements of R2 and this R3 elements minus 2 times R2 we can put. Okay. Why I am doing this? Or simply you can calculate, all are small numbers. Okay. And we can make this element 0, we can simply calculate the determinant, or simply we can get the determinant itself. The first element is 0, multiplied by something 0, so minus 1. Along R1 I am taking. Okay. So the next one is minus 1, and for this the determinant is this 1 4s are 4, minus 6, and then plus 2. Are you there? This is 3 minus 4. So we'll get minus 1 into minus 2 plus 2 into minus 1. So we'll get 2, and this is minus 2, we get 0. Okay. That is the determinant value. Or if you apply like this means, like what we can do, this can be multiplied with 2 and subtracted with this means, we'll get some other things equal and we'll still get the 0. Okay. Any doubts on this? Okay. Also some other way also this thing can be done. Okay. What is it some other way? From here even we can apply the elementary row transformation. We can subtract these two. Okay. These two rows, then we'll get what it is. From this row is subtracted means what I will get 1. I'll do it in that way also. Shall I erase this? Okay. Now we apply the elementary row operations for this one. See, I am going to take the elements of R2 and in the R2 I am going to make a change. R2 minus R1 I am going to do. R2 minus R1. So R1 remains same. 1990, 1991, 1992. Then R2 minus R1. 1991 minus 1990. That is 1. 1992 minus 1991. That is 1 again. Is it? Also, this one, when you subtract 1, are you getting it? Are you there? What happened? Okay. Okay, see, what I did, I simply subtracted these two rows. What I got? 1, 1, 1, right? Like R2 minus R1 I did. The same way, R3 we can write. R3 minus R1 I will take. Not R1. R2 will take. Okay. Now R3 minus R1 is what? 1992 minus 1991. 1. 1993 minus 1992. 1. 1994 minus 1993. 1 again. So we got two identical rows. Answer is 0. Yes. That's what I said. As this is a very first question, I am explaining everything in detail. We can apply two elementary row operations in a single step also. Because what you are going to write, you can rewrite this row and again we should do. That's it. Okay. I get your point. I got your point. Yes. I got your point. Then we'll rewrite better. Like these two have the difference 1, man. These two have the difference 1. Or we can make it with the column. Column also still the same. So if that happens means what it is? This will become 2. Okay, this difference will become 2 and this difference also will become 2. It is not with R2, R1. Okay, you are right. I was wrong. See, 1992 minus 1990 I written. Okay, and then 1993 minus 1991 I written. 1994 and 1992, that is 2. Okay. See, in a hurry I wrote wrongly. Now you see, one row is a constant multiple of other row. If you multiply this with 2, you will get the other. Then what does the property says? If you get one row by multiplying the other row with some numbers, determinant is 0. Simple. This is also one way. This is also one way. Maybe some other way also possible. But the thing is whether we get the determinant right or not. Yes. Yes. See, this row is k times the R2. Simply, R3 is nothing but what? 2 times R2, right? We multiply 2 with this. Okay. If any row is a constant multiple of other row, then we'll get what? Also, there is one more property, one more way. From all these row elements, we can take 2 as common, right? We can take 2 and we'll write all the elements. Here 1, 1, 1. Here also 1, 1, 1. Two identical rows, 0. That property also can be applied. Yes. From this row we can take. Yes. But it is not work in the other way. It will not work in the other way around. Suppose we get the matrix, the number 2 in the outside means we cannot multiply with any of the row. If one row is a constant means we can take it out. Okay. So this property also we can use directly, or we can take 2 as common, or still we can apply the elementary row operations. What it is? What is elementary row operations? I am going to write the result in R3, not R3. Okay, let me write in R3. So what I am going to take is R3 minus 2 times R2 I am going to take. So R3 is what? 2, 2, 2. 2 times R2. 2 times R2 is 2, 2, 2. When you subtract, what you will get? 0, 0, 0. So this entire row will become 0, 0, 0. So again what we will get? If any one row or column becomes 0 means we get determinant 0. Okay. Either way or around, we should be going around all the 10 properties mix and match together. Okay. Got it? Have you understood or not? Now as I explained this might feel easy. But when you work out means you would be really stressed. So you don't stress yourself. First go through all the properties. Okay. Suppose you don't get the idea. You take one question. Try as many steps as you can. It is not necessary that same property should be applied. Here also as you can see we applied so many properties. Okay. So you try as much as you can. Suppose you don't get the answer means look into the solution. Okay. Or else send it to me, we will discuss in the class. Okay. If you wish on this topic we will have one more session like problem solving session. Or else we will go to the next exercise. What we can do? You do one thing, like you just go through this exercise, work it out by yourself, try to figure it out. If you can't figure it out means we'll make one more session of this same exercise for problem solving, and we can tomorrow we have another session, right? And then tomorrow we'll continue the next exercise. Then once this chapter is completed, again we'll get back to here. I think one doubt clarification session we can have. In that session we'll discuss about detail of this exercise. Okay. Now it's about to you whether if you say we can continue with the same exercise of problem solving, we can continue tomorrow, or we can continue with the next exercise. What we can do? Okay, you work out and figure it out. Then based on this we'll do. So as of now, tomorrow we'll start the next exercise. Okay. Okay. Then that's enough for the day, I guess. Do you have any other doubts? Okay. Then I'll see you tomorrow. Take care. Bye bye.